Okay, so Thursday is the first test. So that would be what, 10-6? And the topics are everything up through control volumes. So none of this new stuff I'm going to talk about today. And any tables you need to use, I'll give you the tables. And any equations, there'll be equations on the test, but it's closed book and closed notes. And then before we get into new stuff, is there any, you have any questions on homework or anything? Okay. All right, well, the next thing we're getting into after the test is the second law of thermodynamics. And there are two big things that this is going to help us do, two main benefits. The first is for measuring the efficiency of processes. We're actually going to see that we can actually put pretty sort of surprisingly low limits on the performance of power cycles, refrigeration cycles, even assuming no, friction, thermodynamic versions of friction. So then we'll be able to compare, you can compare actual cycles to these limits that we establish, these mathematical limits. And then the second thing that this can do is it lets us calculate the direction of processes. And, if you think back to the stuff we've done so far with the first law, with conservation of energy, there's nothing in that ever tells us what the direction is of a process. Like if you do a calculation of a skier going down a hill, you say at instant one, the skiers at the top of the hill, at instant two, the skiers at the bottom. How fast are they going at the bottom? But we could have just as easily called this instant one and this instant two and figured out if he's going at this speed, how high up the hill is he going to get. So now for the first time, we're going to be able to use the second law to figure out what's possible. Is it possible to make a process that goes from this direction to this direction? There are three equivalent statements of the second law. They sort of all three have different uses. And at first glance, it's pretty surprising that they're equivalent. Three equivalent statements of the second law. The first one, the most intuitive one, the one that you feel like you could have come up with on your own, or, we probably all sort of have this intuition, we all have come up with it on our own, is called the Clausius statement. And that just says that heat doesn't move spontaneously from a low temperature to a high temperature. So this is the one that, like, all of the second law is based on this idea. And this is the one that's, intuitive. What isn't obvious at all is that based on that Clausius statement, you can prove the second statement of the second law, which is called the Kelvin-Planck statement. Mathematically, you can write it like this. For any system that's in contact with only one thermal reservoir. So a thermal reservoir is just like a big temperature source or sink, big enough that you can put energy into it or take energy out of it, and it doesn't noticeably change the temperature of this reservoir. So for a system in contact with one thermal reservoir, the work done over any cycle by this system is less than or equal to 0. So the meaning of that isn't totally clear right away. But notice that, so what this is saying is, if you have, so think of your one thermal reservoir as like a heat source, a high temperature reservoir. What this is saying is that you can't have a power cycle that's made with only a high temperature reservoir. You can't produce energy, produce work without putting energy out, wasting energy basically in the exhaust at a cold reservoir. Okay, so you can think of this as you can't build a power cycle where all the energy added at the boiler is used to produce work. You can think of that as, that would be like a perfectly efficient power cycle. You pour energy into this machine through the high temperature reservoir, and you'd like to use all that to create electrical energy or to, turn shafts or whatever, but it's not possible. And this can be proved using the Clausius statement. Okay, so the idea is that some of that energy must be lost as exhaust to a cold reservoir. And so this is going to tells us a little bit about what's required for a power cycle, what's required for a refrigeration cycle, and then we're going to use that to define efficiency of these machines, come up with ideal efficiencies that we can compare the efficiency of actual machines to. So what's the benefit of the Kelvin-Planck statement? I said that the Clausius statement is just the one that we have sort of intuitively in our heads. The Kelvin-Planck statement, so I guess you do use this to define performance measures, but really the main usefulness of this is that you can derive the other stuff from it. So from this you derive what's called the Clausius inequality. That's different than the Clausius statement of the second law. And we'll talk about the Clausius inequality in a while. And then from the Clausius inequality, you can define the entropy statement of the second law of thermodynamics. And that's the one that's mathematically going to be the most useful for us in calculations. Really, the main usefulness of the Kelvin-Planck statement is sort of as this intermediate point that we're going to be able to derive a lot of math from. So that's the second statement. And then the third, also equivalent statement, is the entropy statement of the second law. This is the one that you probably, most people probably think of as the second law of thermodynamics. This is the one that says for any process, the entropy of the system plus the entropy of the surroundings is greater than or equal to 0. And this is the one that's going to give us the useful math, really. And by the way, so we need to talk about a little more before we can define what it means to, so if you have a system, what does it mean, the entropy that's in that system? How do you calculate it or measure it? We have to define some stuff before we can do that. But maybe you have noticed that when you look in the tables, there's a column for entropy, specific entropy in those tables. And so for a given material in a given state, there is a fixed amount of entropy. And it's something that you can look up in tables and calculate if you know, say, the pressure and the temperature. Okay, so the first one of these that I want to talk about in detail is the Kelvin-Planck statement. So this is the one that says you can't use all the heat input to a power cycle as work. And we're going to talk about this with a power cycle, refrigeration cycle, and heat pump cycle. So because in a power cycle, you know that you have to have energy lost in the exhaust, a power cycle has to look like this. Here's your system. And here's your hot reservoir. Here's your cold reservoir. And heat comes in to the system from the hot reservoir. I'll call that QH. And heat leaves into the cold reservoir. I'll call that QC. And then energy leaves as work. When we get to refrigeration and heat pump cycles in a second, the directions of these arrows are going to change. So notice that the directions of these arrows are defining a new sign convention for us for this stuff. Okay. So when we're talking about a power cycle, this W means what it's always meant. Like when we were doing the first law, it means energy is leaving through work. But when we talk about the other two, we're going to be inputting work. And we'll see that, a positive W in those cases means work being done on the system. Okay, so be careful about that. The performance of a power cycle so how would you think you would be defining performance? I mean, what's the thing that's a pain to put into a power cycle? The thing that's difficult to put in is the heat from that hot reservoir. The thing you're trying to get out of it is W. And so the efficiency of a power cycle and we'll call that the Greek letter eta, is the work that you produce divided by the energy coming in at the hot reservoir. We can rewrite this because notice that conservation of energy says, if you look at this diagram I have above, the only energy going in is Q sub H. The energy going out is W plus QC. So we know that Q sub H has to be equal to QC plus W. And so you can rearrange this as W is equal to QH minus QC. And so the efficiency then you can write as QH minus QC over QH, which is 1 minus QC over QH. You can already see that we're starting to, there's starting to be some limit to, or you're starting to see that the efficiency is going to be limited. the fact that QC has to be non-zero means that you can't have a perfect efficiency for this power cycle. All right, any questions about that power cycle? So that diagram is something that you're going to want to be able to reproduce from memory. You're going to want to understand the signs of these things so that you can put together this equality that QH is equal to the sum of those other two. And then the other two, so these other two, the refrigeration cycle and the heat pump cycle, are the same cycle. It's just a matter of whether you care about the hot region or the cold region. But we're going to define efficiency differently for them because you have different goals for these things. So refrigeration cycle we have our system, our hot and cold reservoirs. This time, work is coming in. This is the hot up here, the cold down here. And we're trying to get energy to go from the cold reservoir into the system. So Q sub C this time is coming in, and we're trying to get energy to leave into the hot reservoir. So this time, the relationship between these energies, notice that the sign convention is all different. So we have two things going in, work and QC. We have one thing going out, QH. So QH is equal to W plus QC. I guess that's the same equation. It's just that they're going in the opposite directions. The performance of a refrigeration cycle, we'll call it the coefficient of performance. And we'll use the Greek letter beta. Well, if you're thinking about the performance of a refrigeration cycle, what you're trying to do is get as much energy out of the cold reservoir as you can, inputting as little work as you can. And so we'll define this as QC over W. If you rearrange the relationships between the energy inputs and outputs, work is equal to QH minus QC. And so substitute that in for work in the coefficient of performance, and you get QC over the quantity QH minus QC. Notice that when I'm in all the ways that I'm rewriting these performance measures, I'm eliminating work from the equation and just writing it all in terms of heats. It's not totally obvious yet why we're going to do that, but when we start talking about perfect efficiency, we'll see why that is, why this is a useful way to write it. I don't think I've mentioned this before, but do you have a sense for how, like, kind of intuitively how it works to, so we want to take energy from a cold place, bring it into our system, and then send energy out to a hot place. We know from the Clausius statement of the second law of thermodynamics, that's not going to happen on its own. So how do you use the work to make that happen? Do you have a feel for that? Well, yeah. If you so if you have an insulated, piston, say, and you have a gas inside that piston, what's going to happen to the temperature of the gas as you compress it? It goes up. And so if your system is so let's say your cold reservoir is 30 degrees or something, your hot reservoir is 80 degrees, okay? And say you're starting with a gas in your system that's 50 degrees, like right in the middle somewhere. So if you want to get energy from your system out of your system and into that hot reservoir, you compress that piston, get the temperature up, then remove the insulation, let it be in thermal contact with that hot reservoir. If you compress it so that that temperature is 100 degrees, then you're going to lose energy into the hot reservoir, okay? Now you insulate again, let it expand enough that the temperature in there is lower than the cold, the temperature of the cold reservoir. Let it be in thermal contact with the cold reservoir, and now you get energy flowing in from the cold reservoir. And so with that system of constantly expanding, bringing energy in from the cold, compressing, letting energy out to the hot, you can get this energy moving from the cold to the hot. But the cost is the work that you have to do to compress it and let it re-expand. And then the third one is the heat pump cycle. That's exactly the same cycle as the refrigeration cycle, but you have different goals. This time, what you care about is the amount of heat that you're pumping into the hot reservoir. So this looks just the same as the refrigeration cycle. Again, the work is coming in. The way you're using that work is exactly the same. You're using it to take energy from the cold and move it to the hot. This time, the cold is the cold air outside and the hot is inside your house or whatever. And so what you care about is the amount of heat you're bringing into the house. But this all looks just the same. So again, you have QH is equal to QC plus W. And again, we're going to isolate W. That's QH minus QC. The coefficient of performance is the Greek letter gamma. And what we want in this case is we want to add as much energy to the hot reservoir as possible for as little work as possible. So we're going to define this as QH over W. And again, substitute in for work, and you can rewrite this as QH over the quantity QH minus QC. Okay, so now we have, based maybe sort of loosely on the Kelvin-Planck inequality, we have these diagrams of the power cycle, the refrigeration cycle, the heat pump cycle, and we have these definitions of performance of these cycles. What we would like to get to is a set of limits on these performances based on, perfect efficiency in some way. So now we would like to put limits on these performance measures. And we're going to do that by defining reversibility and irreversibility, which is kind of going to be the thermodynamic equivalent of, the way we're used to thinking about friction. It's just ways that energy is just lost and there's nothing you can do about it and you can't get it back. So this will come from defining reversibility and irreversibility. Okay, so let's talk about irreversibilities. About that is thermodynamic friction. And friction actually is included in this list, but there are other things. So let's think for a second, before I get into this list, about like a mechanical system. So you're used to thinking about mechanical systems. So think about like a pendulum that you So you start out holding this ball up at some height, and you let it go. If there's no air resistance, or any kind of friction in the string or anything, once the pendulum reaches the bottom of its swing, It can return to its starting point. That's reversibility. So a reversible system is one where the system and surroundings can return to their starting state. So if you don't have any friction or anything, this pendulum, that's a reversible system. If you have friction, then it's not a reversible system. You lose energy. You can do work to bring the pendulum back up, but that's changing the surroundings. The things that prevent a system from being reversible are called irreversibilities. Actually, this should be a process, not a system. The things that prevent a process from being reversible are called irreversibilities. So now I'm going to give you a list of the irreversibilities, that the things that lose energy from the system and you can't get them back. So any of these things in your system are going to keep your system from being ideally efficient. The first one is friction and air resistance. We're used to those. But now we're going to get into a few that we haven't thought about with like mechanical, with in physics 1. The second one is electric current through a resistance. The third one is inelastic deformation. So if you deform a spring a little bit, you can let it go and it'll return to its length. But if you deform it past that elastic region, you let go of it, it won't go all the way back to its starting, and that's energy that's lost and you can't get back. Fourth is heat transfer through a finite temperature difference. So anytime you have heat transferring over a finite, difference in temperatures, you're losing energy in a way that you can't get back. And it's unavoidable, like you're always going to have to deal with that one, because if you're transferring energy over infinitesimal temperature differences, it takes infinitely long, So there's always going to be energy lost through heat transfer. Five is an unrestrained expansion of a gas. So to avoid this one, at every point in the expansion, the system has to be in equilibrium. So you could do it slowly with a piston system or something, but if a gas is ever allowed to expand in a way that's not at every instant in equilibrium, you can't get that energy back. Chemical reactions, number 6. And then the last one is mixing materials at different states. So I would recommend reading over this list and just, trying to get this roughly in your head. You don't have to be able to list it out by memory, but when these things are mentioned in problems, you should, it should trigger something. Okay. Here are a couple of definitions that you need that are related to reversibility and irreversibility. So 2 important definitions. The first one is a process is reversible if you can run the process in reverse and return both the system and the surroundings to their starting states. The second one is internally reversible. And this one just means that there are no irreversibilities inside your system. So none of the things in that list of 7 ways of losing energy are happening inside your system boundary. Okay, so now that we have talked about irreversibilities, we can talk about the maximum possible performance for power cycles, refrigeration cycles, heat pump cycles. So now we're going to talk about maximum performance. So there are two important corollaries to the Kelvin-Planck statement. The first one is, this one is a little surprising at first, but all reversible power cycles or refrigeration or heat pump operating between the same two thermal reservoirs have the same performance. That's surprising because, you know, you think of all these ways you could rig up systems to produce work by bringing in heat. And you think like, oh, there's got to be good ways to do it and bad ways to do it, you know? Like, couldn't you come up with a way that's just such a convoluted way to produce work by bringing in heat that, you know, it would produce significantly less work for two given thermal reservoirs? But it makes more sense if you think about the fact that we don't have any kind of friction, any kind of things that are losing energy. Like the analogy that makes sense to me is if you think about you're designing a system that turns a skier's potential energy into kinetic energy. Okay. And your equivalent of the thermal reservoirs is just how high a hill you're starting with, okay? So is there a way to, with no friction, produce a better process for turning that skier's potential energy into kinetic energy? Well, if there was friction, there certainly would be. You know what I mean? But without friction, there's nothing you can do. If you're still dealing with those same heights, you could have this skier doing this for 50 miles, and at the end, that skier's speed is going to be the same as if they went straight down the hill. You know what I mean? So that's the deal here with fully reversible power cycles. If you're operating with the same hot reservoir and the same cold reservoir, you're going to produce the same amount of work. And the second surprising corollary of the Kelvin-Planck statement is that all power cycles or refrigeration or heat pump cycles with irreversibilities, with any irreversibilities, have worse performance than reversible cycles. So what this says is if you can come up with any kind of reversible power cycle that you're capable of doing calculations on, that can give you an upper limit for performance for any actual existing power cycle. Okay. And I'm not going to talk about this much right now, but the most studied reversible power cycle is called the Carnot engine. And different people start this cycle in a different place and whatever, but I'm going to start it like this. It's an isothermal expansion. I mostly just want to get this in your notes. We're not going to use this. Followed by an adiabatic expansion. You know what isothermal and adiabatic are? Isothermal means same temperature. That makes sense, right? So the temperature doesn't change, constant temperature. Adiabatic means no heat transfer, so that's like well insulated. And then an isothermal compression. And then an adiabatic compression. So this is a simple power cycle that lends itself to looking at mathematically, and using that you can come up with performance measures that you can compare to actual things, and it gives you sort of an upper limit for the performance of power cycles. Now, we're almost to sort of the payoff of this. It's been a lot of just talking, but we're going to get to stuff where we can actually do some calculations. The definition of the Kelvin temperature scale is for a reversible power cycle. the ratio of the heat that's lost in the exhaust over the heat that's added at the boiler is equal to the ratio of the temperature of the cold reservoir divided by the temperature of the hot reservoir. So the ideal performance, since this is defined in terms of a reversible power cycle, and we know that a reversible power cycle has the best performance you can have, that means that the ideal performance for a power cycle is, remember this is the definition of the performance of a power cycle, 1 minus QC over QH. We came up with that before. And so the maximum is that where you replace QC over QH with TC over TH. For a refrigeration cycle, our definition was QC over the quantity QH minus QC. And that gives us that the maximum performance for a refrigeration cycle is the temperature of the cold divided by the quantity temperature at the hot minus temperature at the cold. And then for a heat pump cycle, before we defined gamma as QH over the quantity QH minus QC. And so that gives us that this maximum performance for a heat pump is the temperature of the hot divided by the quantity temperature of the hot minus temperature of the cold. Okay, so let me just do 2 example problems where we use this stuff. So basically what this is going to let us do is for a given pair of temperatures at the 2 reservoirs of your heat pump cycle or refrigeration or whatever, it'll let us determine how much power you can get out of the system or how much power you have to add to it if everything is perfectly efficient. And, I mentioned at the beginning that these are actually, to me, they're sort of surprisingly tight restrictions, useful restrictions. Okay, so let's say we have a power cycle. With a boiler temperature TH of 500 Kelvin. Remember, when you're doing these ratios, these have to all be in Kelvin or in some absolute scale. And the exhaust temperature or the temperature of the cold reservoir is 300 Kelvin. And let's say that we have 1,000 kilowatts delivered at the boiler. is it possible to get 450 kilowatts of power out of this system? Okay, well, the definition of performance for a power cycle was, we can write it two ways. One is the work divided by QH. And the other way is 1 minus the heat at the cold reservoir divided by the at the hot. The maximum possible is 1 minus TC over TH. And so that's 1 minus 300 over 500. So 0.40. Well, we're asking if we can get 450 kilowatts of power out. That's the work. So I'm going to use, work over QH is equal to 450 over 1,000. That is 0.45, which is better performance than 0.4. So it's not possible. Questions about that one? I have another example here that's, just using a refrigeration cycle. And also the other thing about this other example is that it's using Celsius temperatures instead of Kelvin temperatures. Remember, that means you have to convert when you're doing these. If you do these with Celsius or Fahrenheit temperatures, it's not gonna work at all. So I think maybe I'm not going to go through this, but just remember to do those conversions. And if you're doing a refrigeration cycle or a heat pump cycle, you just have to use those different measures of performance. So for refrigeration, you'd have to use beta and beta max, but it would be the same approach. All right. Well, I'm going to stop there. But the next thing we're going to do after the test, so test on Thursday, and then we're going to start moving from the Kelvin-Planck statement of the second law into the one that's really going to be the thing we care about the most, which is the entropy statement of the second law. And we'll see how those two things end up being equivalent. We'll define entropy and that kind of stuff. So that'll be next Tuesday. Any questions? All right, see you Thursday.